For this part of the class, we will talk about calorimetry. Okay, what is calorimetry? What is it used for, and all that stuff. In the nutshell, what calorimetry is is based on the conservation law of energy. So what is happening in the calorimetry is something like this. We have the system. I will just do a schematic view of calorimetry. We have the system. And as I said, what is happening in the system is a reaction system, a chemical reaction, okay? A chemical reaction is happening. And then this is surrounded by usually water. Okay, so here we have water surrounding. So then we have some types of insulation that is happening here. So this is closed, and then we have a thermometer that we are adding here. And the technology of calorimeter is so advanced nowadays, but the basic of it is that whatever is released or absorbed by the system, also known as the chemical reaction, it is either absorbed or released to the surrounding. Where do we base this? We base this in the conservation law of energy. Remember what the conservation law of energy is saying? That the energy is not absorbed, is not released, or the energy is not destroyed, is not created, but it is transformed from one form to the other. So, in other words, in an isolated system, the energy is not created, is not destroyed, but is transformed from one form to the other. And what are those forms that are transformed? From the potential energy of the chemical reaction to, to the surrounding. Okay, it's an exchange that is happening between the surrounding, which, as I said, usually is water, and the chemical reaction. What is that change? If the system, also known as a chemical reaction, is releasing, then the surrounding, which in most of the cases, in 99% of the cases, is water, surrounding is heated up, is warming up. How do we notice that? The temperature is increased. Okay? And if the system, which is the chemical reaction, is absorbing, then where is it absorbing from? From the water. Then the surrounding, which is the water, is cooled down. How do we notice that? We notice and we see that the temperature is going down. It's going down to close to zero or less than zero. Okay. The notice is in the surrounding, but it is as a result of the change that is happening in the reaction. Now, the way that we measure the change of the heat change that the surrounding is going is using the formula Q is equal to mc delta T, where Q is the heat that either is absorbed or released in the surrounding. M is the mass of water, usually is water, that is in the surrounding of calorimeter. C is specific heat. We'll talk about this in more detail. Specific heat capacity. And delta T is the change of temperature in degrees. Change of temperature in degrees. Okay. So the units for mass are in either grams or kilograms. Specific heat capacity units are joules per kilograms times degrees Celsius, or joules per grams degrees Celsius, depend on what it is. And change of temperature in degrees is the units are degrees Celsius, leaving us the heat to be in joules or sometimes kilojoules. Okay, so now we are making a conclusion. We are drawing a conclusion as to what is happening in the reaction based on the conservation law of energy, that is saying whatever is happening in the reaction is reflected in the surrounding, and then we are measuring that is happening in the surrounding using Q mc delta T. Now, specific heat capacity, C, is telling us what is the heat, what is the energy that you need to inject or absorb from 1 gram of material, matter, to change the temperature by 1 degree Celsius. Okay, so when we are mentioning that the specific heat capacity of water is 4.19 joules per gram degree Celsius, that means that you have to inject, you have to add into 1 gram of water to change the temperature by 1 degree Celsius, 4.19 joules. The higher the number, that means that the more heat you need to add into the material. The less the number, less heat you need to add or absorb or attract, take away from the material to either heat it up or cool it down by 1 degree. Okay. However, when we are working with calorimetry, there are some assumptions that we have to keep in mind. So the very first one is that we are dealing with an isolated system. Remember what we said in terms of the isolated system, that the system cannot, the matter, mass, and the energy cannot be moving out of the calorimetry. So whatever is happening in the reaction is transformed into the surrounding, and then this is not going anywhere else, but it's staying there. Okay, so this is the very first assumption that we are doing into when we are dealing with the calorimeter. We are dealing with an isolated system. In other words, the heat is not transferred from the calorimeter into the air, I suppose. The second one is that we are thinking and we are assuming that the conservation law of energy is true, meaning that the energy released or absorbed from the reaction is all going into the water of calorimeter. So conservation law of energy is true. There is no loss when the exchange of energy between the chemical reaction and the water. The third one, which is something that you have to keep in mind, is that the density of water is 1 gram per 1 milliliter. So it means that 1 gram of water is equal to 1 milliliter of water. So usually we measure the volume of a liquid into milliliters, but for water, 1 milliliter is equal to 1 gram of water. The next assumption that we do here is that when we have a aqua solution, the density of the aqua solution when we are dealing with or when we are treating it from the specific heat capacity will be the same as water. So I will say here specific heat capacity of an aqua solution is equal to specific heat capacity of water as 4.19 joules per gram degrees Celsius. Okay, and then even when we are working with a calorimeter, another assumption is that the lead and the steer of the calorimeter does not absorb any energy. So those are the assumptions that we have what we have in place when we are working with calorimeter. And then what we will see now is the principle of calorimetry. So again, the nutshell of calorimeter is that you see what is happening in the surrounding water and you draw the conclusion what is the enthalpy change. Enthalpy, remember what it is the internal energy of the system. What is the enthalpy change of the reaction? So you think the surrounding the temperature is increased, then this increase of temperature, change of heat of the surrounding is as a result of the energy that is released from the chemical reaction to water. And the other case is you notice that the temperature of water is dropped, meaning that it's cooled down. That means that this energy that water had was absorbed by the chemical reaction. Now, we said that we have two types of energies, the potential energy and kinetic energy. In the general definition of kinetic energy is that every particle that is moving and has a mass, it possesses a kinetic energy. And the same thing is happening here with atoms and molecules. But on top of that, they have even rotational and translation motion, the molecules, which adds into kinetic energy. Potential energy in a chemical bond or in a chemical reaction is as a result of the bonds that the chemical reaction has Remember what we said, either molecular or ionic compounds, and the intermolecular forces. So the forces between the atoms and between the molecules. It is very difficult to measure the um, potential energy or kinetic energy of all the particles that are dealing in the chemical reaction. Therefore, what we do is we measure the enthalpy change. The enthalpy change is known as delta H. H is for the enthalpy, and it is equal to the enthalpy of the product minus the enthalpy of the reactants. Remember that the chemical reaction has two parts, reactants and products. So the enthalpy of the product minus the enthalpy of the reactant is known as the change of enthalpy of the product, okay, of the system, sorry, of the system. So we have two parts here. We have the heat that we can measure of the surrounding, that we can measure it using mc delta T. This is surrounding. And then on the other hand, we have the system. That is the change of enthalpy, which is the enthalpy of the product minus the enthalpy of the reactant. This is the system known as reaction, okay, chemical reaction that is happening. Based on the conservation law of energy and the assumptions that we did in calorimetry, we say that those two are equal to each other, okay? Because in an isolated system, the energy is not created, not destroyed, but it is, now we say, for this specific case, released or absorbed by the chemical reaction, and it is transferred to the surrounding, okay? So mathematically, we support our calculations based on the fact that the energy lost, whatever part is happening, is equal to the energy gained. And if this lost is from the surrounding, then we say QMC delta T. If this lost is from the system, then we say delta H. And if the gain is from the system, we say delta H. If the gain is from the system, then we say delta H. Do you understand? Before we move to specific examples, I want to talk a bit about that is known as the molar enthalpy or molar enthalpy change of the reaction, or what molar enthalpy. So when we have an amount that is dealing in the reaction, and then as a result of this, we have a certain amount produced in the products, and we see what is happening in the surrounding, in water, then we are dealing with that is known as the molar enthalpy, enthalpy change of reaction. So to say that is the reaction, we have the letter R here. So this is the indication that we have for the enthalpy change of reaction. And the units for it are either joules or kilojoules. So are the units of energy, because those are the units of energy. But a concept very often we want to find what is the change of enthalpy per unit of moles. So the change of enthalpy per units of mole is known as the molar enthalpy change. And this is with a subscript m to represent the molar. And the units for it are either joules per mole or kilojoules, depend on what it is per mole. If it is too big, then we usually say kilojoules per mole. Okay, so the enthalpy of the reaction, is calculated as number of moles times the change of enthalpy per mole, where N is the number of moles participating in the reaction. And here is where we come to the mass to mole, mole to mass, the skill that you need to know. Now, putting all of those together now, using the fact that calorimetry is assuming that the conservation law of energy is true, that the energy absorbed or released from the system is completely transferred to the surrounding, and all the other things that we talked about, then we can say that Q, which is the energy of the surrounded that is measured as mass, and I will say water here just to make the distinguish, mc delta T is equal to the change of enthalpy of the reaction, which in other words is number of moles times the molar enthalpy of the reaction. So this is the formula where we will derive and use to deal with questions that are on the nutshell they have calorimetry.